Hey folks, this is the second video on deriving kinematics equations. We're focusing on the second and the third equations. The second equation builds upon the first one and the fourth one. So if we take like the area under this graph to be the displacement, we arrived at, for the fourth equation, we saw that the displacement was equal to 1/2 the sum of the initial and final velocities times time. And so the other thing we want to keep in mind is that we have a separate equation already for final velocity. So Vx equals Vx naught plus Ax times time. And so these are two algebra-based derivations. If I can combine these two equations and I can eliminate final velocity and introduce acceleration, I can get to this second equation. So I'm going to perform a substitution. We do this a lot in physics. Vx is described by this quantity, so I'm going to substitute it in for the Vx in the displacement equation. So I get delta x equals 1/2 times Vx naught plus, and then Vx is equal to Vx naught plus Ax times time. And then the other side, I have it multiplied by time. I'm not going to go through each algebraic step, but basically, like, I can talk about it. There's two Vx naughts that when you multiply them by 1/2 and by t, you get Vx naught times time. So that's the first term of the second equation. And then if you take Ax times time and multiply it by 1/2 times time, you get 1/2 Ax times time squared. Now remember that delta x is really x minus x naught, and so you can add x naught to both sides and you end up with this equation right here. So that's our first derivation, basically taking equations we already know and performing a substitution. So that's great. And then the fourth equation is, more pure algebra. So we take like two different equations and use them together. So we're going to start with an idea we talked about earlier in the previous video, that the displacement of an object is equal to the average velocity times time. And I'm going to take Vx equals Vx naught plus Ax times time, and use that equation also. In fact, I'm just going to skip a step and I'm going to rewrite this displacement equation. Delta x equals 1/2 Vx naught plus Vx times time. And so I can substitute this equation into this equation. So the fourth equation doesn't have time. So the idea is I want to solve this equation for time. And what I get is Vx minus Vx naught over Ax. So I now take this quantity, substitute it in for time, and rearrange it to find that it's the third equation. So I go delta x equals, since this is written like a fraction, I'm going to write this like a fraction, Vx naught plus Vx over 2. So that's this equation without time. And then time is equal to this, so it's Vx minus Vx naught over acceleration. And so, you might remember from algebra that this is a situation where if you FOIL it or make it into a polynomial, you get something rather special. And so delta x equals Vx squared minus Vx naught squared over 2ax. And so I can just rearrange a couple of things and turn it into this equation. I would multiply both sides by 2ax. I get Vx squared minus Vx naught squared equals 2a times delta x. And then if I add this to the other side, I get this equation. So the first derivations were mostly based on graphs. These last two are just based on algebra. And they're all intertwined. I could have done this a number of other ways, but all of this is the same physics, just manipulated slightly. And that's that.